Before we take a look at the 6 reciprocal identities, which you already kind of know, let's recall SOHCAHTOA. Right, SOHCAHTOA, where sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent is opposite over adjacent. So do you remember the reciprocal function of sine? Right, if you have hypotenuse over opposite, do you remember which one that was? Right, it's cosecant. What about for cosine? What's the reciprocal of that? If I had hypotenuse over adjacent, that is secant. And the reciprocal of tangent, right, would be cotangent. So here are the 6 reciprocal identities. Notice that they're just reciprocal functions of each other. The 2 that you are going to use the most are these. Cosecant theta equals 1 over sine theta, and secant theta equals 1 over cosine theta. Basically, if you see cosecant theta, you're most likely going to want to replace it with 1 over sine theta. If you see secant theta, replace it with 1 over cosine theta. Occasionally, you will also use cotangent theta equaling 1 over tangent theta as well. There are 2 identities called quotient identities. Remember, quotient is just the answer you get from dividing. Tangent of theta can be represented as a quotient, 1 over cotangent like we saw earlier, but there's another one. Do you remember from the left-hand trig and just from class what we mentioned from the unit circle? Right, it's sine of theta over cosine of theta gives you tangent of theta. So that means cotangent of theta would be what? Right, cosine theta over sine theta. These 2 quotient identities will be used a lot as well. So sometimes if you see tangent theta, you want to replace it with sine over cosine. If you see cotangent theta, you'll want to replace it with cosine over sine. To show you why this works, let's take a look at tangent theta. Remember, we have TOA, and we have sine, which is so, and cosine, which is ka, right, for the SOHCAHTOA. So tangent theta, right, is equal to opposite over adjacent. And that is equal to sine, which is opposite over hypotenuse, over cosine, which is adjacent over hypotenuse. Notice that we have O over H divided by A over H, which is O over H multiplied by H over A. The H's cancel out, and you end up with OA, right? O over H. Right, so these are identities. They're actually equivalent to each other. Same thing with cotangent theta and cosine over sine. Let's take a look at the Pythagorean identities. Note that the word Pythagorean, right, from Pythagorean identities looks like Pythagorean theorem, and there is a connection to that. Let's consider the unit circle where your radius is equal to 1. Recall that if I have a point on the unit circle x comma y, I'm able to create a right triangle here, where the horizontal distance to that point would be x, the vertical distance to that point would be y. And using the Pythagorean theorem, we know that x squared plus y squared is equal to 1 squared in this case, right? Because it's a unit circle where the radius or hypotenuse is equal to 1. Also recall Sir-Kixer-Tykes, right? Sir-Kixer-Tykes is really the trig ratios, the trig functions, SOHCAHTOA, written in terms of x, y, and r. So remember, because our radius is 1 in a unit circle, sine theta is really equal to the y, right, because it's y over r, and r is 1, and cosine theta is equal to x over r, or x over 1. So recall that x comma y is equal to cosine theta comma sine theta in a unit circle, and that's why it makes it so convenient to have the unit circle filled out in front of you to answer a bunch of questions. In this case, notice that we can replace the x and the y with cosine and sine. So I've gone ahead and replaced the x with cosine theta and the y with sine theta. And when we square it, the notation is when we square the entire cosine, that square can be written right here. So I can rewrite that as cosine squared theta. In fact, that's how you're normally going to see it written. Same thing with a sine squared theta. Instead of writing as sine theta quantity squared, you'll see it written as sine squared theta. So this is the first of the 3 Pythagorean identities. It's really Pythagorean theorem written in terms of cosine and sine. One thing to note is that cosine theta squared does not equal cosine squared theta, right? Cosine squared theta is equal to cosine theta quantity squared. Right here, cosine theta squared, that would be cosine of theta squared. Where here, it's the entire cosine being multiplied by itself here, it's just the theta being multiplied by itself. Okay, so again, we have our first Pythagorean identity. Cosine squared theta plus sine squared theta is equal to 1. You'll often see it written this way in this order. Sine squared theta plus cosine squared theta is equal to 1. That's the standard way of writing it, but either way works. Now let's say we wanted to divide every term by sine squared theta. What happens if I divide everything by sine squared theta? Okay, sine squared theta over sine squared theta, that's just 1. And now what would cosine squared theta over sine squared theta be? Well, recall off to the side that cosine theta over sine theta is equal to, by the quotient identity, cotangent theta. Notice that if I were to square both sides, right, on the left-hand side I would get cosine squared theta over sine squared theta. On the right-hand side I would get cotangent squared theta. So I can replace cosine squared theta over sine squared theta with cotangent squared theta. Now let's take a look at 1 over sine squared theta. Recall that by the reciprocal identity, 1 over sine theta is equivalent to cosecant theta. And again, if I were to square both sides, notice that on the left-hand side I get 1 over sine squared theta. On the right-hand side I get cosecant squared theta. So I can replace 1 over sine squared theta with cosecant squared theta. And this is our second Pythagorean identity. So here's a way that can hopefully help you remember this particular identity more quickly, and that's by thinking of I caught a fish. So as I caught with a bad spelling, and then fish, visualize this as a fish. This time let's divide by cosine squared theta on both sides. And this would give me, right, sine squared theta over cosine squared theta would give me tangent squared theta. Cosine squared over cosine squared is just 1. And then 1 over cosine is secant, but since it's squared, it's going to be secant squared theta. And this is our third and last Pythagorean identity. So a little tip to help you remember this one is get a tan in 1 second. Tan in 1 second. Let's do a recap of the Pythagorean identities. Sine squared theta plus cosine squared theta equals 1. That one's a pretty easy one to remember. What about the other ones? I caught a fish. So I caught a fish. Remember, all of these are squared terms individually. The third one is tan in 1 second, right? Tan in 1 second. Again, notice that each of the terms are squared, right? 1 squared is just 1. So here's what you need to be able to do after this lesson. Use trig identities to transfer one side of the equation into the other. So I have a left-hand side and a right-hand side. I would choose the one side where it looks like you can do more with it. So I'm going to go ahead and choose the left-hand side, and I'm going to only work on the left-hand side to make it look like the right-hand side. Well, I have cosine theta and secant theta. You want to replace any terms with one of the identities. So remember, secant theta, I can replace that as 1 over cosine theta. And when I do that, notice that cosine thetas cancel out, and I get 1 on the left-hand side, and that matches the right-hand side. So you know that your final answer on the left-hand side is going to be 1 because we need them to equal each other. But it's the process that needs to be correct. Here's another example. So I have more stuff going on the left-hand side, so that's what I'm going to work on. So I'm going to do a bunch of work, and at the end it should equal 1 on the left-hand side as well as the right-hand side. So what could I do on this left-hand side here? Notice that I can try to FOIL, right? If I FOIL it out, I get secant squared theta, right? The two middle terms are going to cancel out because I have negative secant theta tangent theta, and I have positive secant theta tangent theta. All right, so the middle terms are going to cancel out, and I get minus tangent squared theta. All right, I have a difference of 2 squares. These two terms are conjugates of each other, so the middle terms are going to cancel out. So on the left-hand side, I am left with secant squared theta minus tangent squared theta. Now what can I do at this step here? Notice that I have secant squareds and tangent squareds. Recalling the Pythagorean identity, so I would definitely have all of the identities listed out in front of you on a separate sheet of paper. I see that tangent squared and secant squared theta are both used in this equation here, tan in 1 second, right? So you can replace secant squared theta with tangent squared theta plus 1. When I replace secant squared theta with tangent squared theta plus 1, because those are equivalent, right, by the identity, notice that I can cancel out the tangent squared thetas, giving me just 1. So I get 1 is equal to 1. Alright, here's the last example. We have a left-hand side and a right-hand side, and I'm going to work on the right-hand side because it looks like there's more going on there. I will tell you with these types of problems, there's often more than one way to show your work. So there's often more than one way to be able to simplify this to make it look like the other side. However, there's usually one way that's more efficient than the rest. When I see this right-hand side and I see 1 over sine squared theta, I immediately think of something. I can replace it with cosecant squared theta minus 1 using the reciprocal identity. And when I see cosecant squared theta, I recognize that from this Pythagorean identity here. So I'm replacing cosecant squared theta with 1 plus cotangent squared theta. And when I do that, notice that the 1's cancel out here, leaving me with just cotangent squared theta, and that's what I was going for. Notice here when I saw the cosecant squared theta, I also could have thought of 1 over sine squared theta, the reciprocal identity. But then that wouldn't help me because I would go back to the previous step. So when you look at your identities, you may try to plug in 1, and if that doesn't get you closer to what you're going for, then try a different identity to plug in. So here are the identities that you'll use most often. Secant theta is 1 over cosine theta, cosecant theta is 1 over sine theta, tangent theta is sine theta over cosine theta, cotangent theta is cosine theta over sine theta. But notice that if I were to square both sides, right, I would end up with these as well. Secant squared theta is equal to 1 over cosine squared theta and so forth. Also recall sine squared theta plus cosine squared theta equals 1. I caught one fish, right, or I caught a fish, and tan in 1 second. But remember that the Pythagorean identities, you need to have those squared terms. So for example, if as part of my step that I'm trying to simplify or substitute, I see cosecant squared theta, I may want to replace cosecant squared theta with 1 plus cotangent squared theta, or I may want to replace it with 1 over sine squared theta. It depends on what's going to help me simplify further to make it look more like the other side. Sometimes you can substitute it and things will cancel out right away. Other times you may have to combine fractions by getting the common denominator. So you have two fractions and you rewrite them as a single fraction. Other times you may have to separate into two fractions. So you might have a single fraction and you separate into two separate fractions and then substitute. You may have to FOIL and then substitute, or you may want to factor and then substitute using the identities. Just a heads up that the next chapter, chapter 5, deals a lot more with these identities, plus more formulas. So I would definitely take the time now to get really comfortable and confident with using these fundamental identities.